today is solving the problem of microplastic evolving recycling technology. We have very interesting speakers today about from our sister projects, Greenland, Uplift, Preserve, and of course from the upPE-T project. Fuensanta Monzo is the project coordinator from the upPE-T project from the CETEC organization. He's going to do an introductory speech about the theme of today and explain the importance of the project's collaboration. Natasa Stojic is the Associate Professor at the Faculty of Environmental Protection at Edukons University and is representing Greenland project. Natasa is going to speak about microplastic as an emerging environmental pollutant. Debolina Paul will follow with a presentation about sustainable upcycling of plastics for circular economy and greener environment. She works for DGOTouch and also is partner of the upPE-T project. Following the three presentations, we'll have a break, and then in a speech from Boku University, who also works for upPE-T project, will do a presentation about how microbial communities use polymers as substrate. Then Valentina Bisinella, who's an associate professor at the Department of Environmental and Resource Engineering at the Technical University of Denmark, is going to explain how Uplift's sustainable solutions for plastic bioupcycling are. And then Teresa Calvo, who's the project manager in the Packaging Materials Transformation Unit in ITNE, representing Preserve projects, will explain finish coatings to reduce microplastics released from recycled textiles. The agenda is quite full. We've got 3 hours. As I said, following the first three presentations, we will have a break. Then there are 2 more presentations from upPE-T and Uplift. We will have another 10-minute break, and then we will have the final presentation from Preserve with some concluding remarks from Natasa Stojic from the Greenland project. As you may notice, the webinar is being recorded. We have muted all microphones because we have quite a lot of registrants today, so it's not going to be very noisy. If someone wants to make a question, they can use the chat box, or they can raise their hands by clicking on the reactions button at the bottom of the Zoom application. They will be asked to be unmuted. Each presentation lasts for 20 minutes, and then there will be time for questions and answers followed each presentation, as well as during the webinar. They can use the chat box, and we will have some opportunity at the end for people that for people to make comments or raise any more questions. So now I will hand over to Fuensanta in order to do the introductory speech. So Fuensanta.
Thank you, Angela. First of all, I want to thank upPE-T partner, the Institute for Development and Innovation in Serbia and Greenland project, for organizing this webinar, and also our sister projects, Uplift and Preserve, for participating as speakers, as well as upPE-T partner DigiTouch and the University of Boku. This webinar is one of several joint webinars that we organize as a result of the collaboration between different projects as part of upPE-T clustering activities. In upPE-T, we think that sharing knowledge and finding synergies between projects will enhance the quality of our outcomes and will contribute to reaching a higher number of stakeholders and audience. A good example of these possible synergies is our collaboration with Greenland Project, who are addressing the important problem of microplastic accumulation in natural environments. In fact, in the first meeting we had with Greenland, we could clearly see how the technologies and products developed in the frame of upPE-T, uplift, and preserve can contribute to the reduction of microplastics. So this is a topic that we are discussing in this webinar, and I invite all of you to bring up your questions and to participate in the discussion in order to enrich the final pictures of possible synergies between all of us regarding possible solutions to be found for this important topic of bioplastics accumulation. And I thank all of you to attend this webinar, and I give the word again to Angela.
Thank you, Fuensanta. So we are starting the webinar with our first presentation. So I will hand it over now to Natasa Stojic from Greenland Project. Natasa. Natasa.
Thank you very much. Do you hear me? Thank you, Angela. Thank you, Fuensanta. It is a great pleasure for me to be here with all of you and to present Greenland Project. Greenland Project is a Horizon project and started in January this year. And we are working on building capacity for our institution, for University Educons in the field of microplastics. So my presentation today, sorry, just to put in presentation mode, is about microplastics as an emergent pollutant, environment emergent pollutant. First, some common informations about microplastics, because my presentation is the first one. So first about definition about microplastics. The most commonly used definition, as you all know today, is that microplastics are plastics fragments with size less than 5 millimeters, or plastic particles of plastics that are either intentionally manufactured, such as microbeds, or result from the degradation of larger plastic items. However, a large number of scientists question the accuracy of this definition. If you ask me, we know that micro is the prefix of a unit in the metric system. That means millionth of a meter. So according to me, the label micro for particles with dimensions in millimeters is unacceptable, but that is theme for maybe another webinar. In the last 20 years, different definitions of microplastics have emerged. In 2004, Thomson used the term microplastic to describe the accumulation of microscopic pieces of plastic in marine sediments in the water. Then in 2009, Arthur and his associates proposed an upper size limit to the initial term, and microplastics were known as plastic particles smaller than 5 millimeters. After 2 years, in 2011, Cole distinguished microplastic according to their origin into primary and secondary microplastic. Sorry. Then in 2015, the joint expert group defined microplastics as plastic particles less than 5 millimeters in diameter, which also includes particles in the nano-size range of 1 nanometer. And this helped to further expand the definition worldwide. In 2020, ISO standards define microplastics like any solid plastic particle insoluble in water with dimensions between 1 micrometer and 1,000 micrometers. Microplastics have recently been identified as an important emergent global problem, which affects marine organisms, but also the humans. There has been a significant increase in the concentrations of microplastic particles in the surface water of oceans with the last 4 decades, and concern about the potential impact on the marine environment has increased during the past few years. But we cannot say that microplastics were not present even 20 or 50 years ago. But lately, a large number of scientists have started analyzing its presence in the environment, and we have become aware of its harmful effects. Plastics is very versatile material and which is used for the production of some modern products, such as cosmetics, dishes, construction materials, packaging, and in some medical devices. And although there has been a strong recommendation in recent years to ban single-use plastic and develop recyclable packaging products, particularly as a part of EU plastic strategy and circular economy action plan, plastic disposal still remains a key environmental challenge. Projections are that by 2050, another 33 billion tons of plastic will be generated worldwide. So global plastic resin production has increased from about 1.7 megatons in 1950 to 368 megatons in 2009. With an average annual growth rate of about 3.5% since 2011. Here we can see annual per capita consumption of plastic resin, and that varies between regions, estimated in 2050 to almost 140 kilograms in the North American Free Trade Agreement and Western Europe. Then, as you can see, 108 kilograms in Japan, 36 kilograms in the rest of Asia, and 16 kilograms in the Middle East and Africa. This wide range in consumption underscores the potential future growth in plastic consumption worldwide, and assuming annual growth levels of 2% or 4%, would lead to global plastic production levels of 680 or 1,240 megatons in 2050, as is shown in this figure on this slide. According to the last report of Plastic Europe, everyday plastic use has shown an exponentially increasing trend for production and consumption, reaching about 350 million tons in 2009. Employed in the European plastic industry are more than 1.56 million people in 5,050 companies with over 350 billion euros of turnover. As you can see on this picture, plastic producers are spread worldwide, and the biggest contributors being Asia, Europe, and North America. Now some basic informations. Microplastics are divided into 2 types, primary and secondary microplastics. Examples of primary microplastics include microbeads found in personal care products, plastic pellets used in industrial manufacturing, and plastic fibers used in synthetic textiles. Primary microplastics enter the environment directly through any of various channels, for example, product use, then unintentionally loss from spills during manufacturing or transport, and so on. Secondary microplastics form from the breakdown of larger plastic. This typically happens when larger plastics undergo weathering through exposure, for example, wave action, wind abrasion, and over-radiation from the sunlight. Studies of the potential ecotoxicological impact of microplastics have been varied, but many have shown harmful effects when these microplastics are associated with persistent organic pollutants, with POPs. This mainly refers to the sorption and transport of POPs by microplastics in the aquatic environment. Indeed, the association between microplastics and persistent organic pollutants are very common in the environment, and if the mechanisms of interactions are well known, they depend on many factors, and their significance in the environment can be very variable in time and space. These interactions depend on both the plastic particle, for example, what polymer type we have, what is particle size, shape, specific area, and so on, and the pollutant characteristic like hydrophobicity, functional group, and so on. But also environmental factors are very important, like microorganism population, pH, dissolved organic matter, concentration, temperature, and so on. However, except in specific situations, the role of microplastic as a local source of persistent organic pollutants is rarely significant due to the limited amounts of pollutants that are involved here. But the impact of endogenous chemicals that enter the initial composition of plastic, like phthalates, biocides, and so on, is much more significant. Studies have shown numerous impacts of microplastics on terrestrial, marine, and freshwater organisms. And toxicity appears to be mainly due to damage to cell membranes and oxidative stress. Findings in this area are mostly laboratory-based, using model organisms and exposure to relatively high concentrations of microplastics. Since ingestion is the dominant route of human exposure, many studies have focused on the behavior of micro and nanoplastics in the gut. Ingestion can lead to systematic exposure if a micro or nanoplastic can cross the intestinal barrier and distribute to tissues and organs via bloodstream or lymphatic system. Some scientists also found PS nanoparticles in human intestinal cells exposed to a range of concentration for 24 or 48 hours, but did not observe significant toxic effects. Also similar to the results of another study in which brain and epitel cells were exposed to PS nanoparticles. In another experiment, human lung epitel cells exposed to 25 nanometers and 70 nanometers PS nanoparticles suffered negative effects. However, when scientists exposed human lung cells to 20 and 200 nanometers PS nanoparticles for 28 days, they found that healthy respiratory cells adapted to low levels of repeated exposure. So the conclusion of these studies is that the effect of micro or nanoplastics on human embryon cells or on human cells deserve further detailed investigations. One of the biggest problems when analyzing microplastics, especially microplastics in soil, is that there is currently no standard method. That is, each laboratory has its own method. So we are now coming to the goal of the Greenland project. Goal of the Greenland project is to increase capacity of our university, of our faculty in the field of microplastics. And given that the biggest problem is the extraction of microparticles from soil samples, We will devote the next period to searching for the best conditions for extracting microparticles in our laboratory, of course, in cooperation with our project partners. On this slide, authors showed the entire process of microplastic analysis, from sampling to instrumental analysis, which I will discuss about it on the following slides. The method of microplastic sampling depends on the source, pathways, and matrices, and each of these variables calls for a different set of considerations regarding level of replication or number of study sites and coverage, as well as controlling for background contamination to general and matrix-specific quality assurance, quality control measures. It is most important at the beginning of this process to prevent cross-contamination and to ensure accurate results, and so that we must carefully implement some procedures for each matrix. If we do not take appropriate precautions during sampling and analysis, environmental samples can be contaminated by plastic particles from external sources. So it is very important to have quality assurance and quality control measures. And as you can see on this slide, there's some inconsistency in methods. Even in this first step, that is during sampling, some laboratories prefer glass, other stainless steel containers. Some researchers are working with composite, other with grab samples. Also, there is a difference in the amount of sample. It ranges from 5 grams to 1 kilogram and so on. That is only in sampling. The next step is sieving. Sieving separates microparticles from soil, sand, sediments based on particle size fractions, and is usually a pre-treatment procedure used to remove particles larger than 5 millimeters. Next step is filtration. Filtration is a technique of separating the solid phase from the liquid phase using a filter which is with a certain pore size. When we talk about filters, also there are researchers and laboratories some laboratories are using aluminium, ceramics, some polycarbonate filters, material for filters, but it is very important here to have in mind that it is very important size of filter pore membranes. Next step is density separation, and sodium chloride is most often used because it is cost effective and environmentally friendly. But besides sodium chloride, also is used sodium iodide, sodium bromide, zinc chloride, and some other solutions. One of the greatest challenges for microplastic detection is distinguishing between plastic and naturally occurring particles. And before analysis, it is necessary to remove organic matter from complex matrices. Also, there are many methods for removing organic matter from these soil samples, and some of them are on this slide here. At the end, we are coming to instrumental analysis, and when we talk about instrumental techniques, there are also different opinions as to what is the best and most precise, and in another hand, economically available technique. And on this slide, you can see some instruments that can be used for instrumental analysis for microparticles. And on this slide that will be presented later, we will see which techniques were used during the research conducted by the GRS. Some problems occurred and are observed during the analysis of soil samples, and they are presented here. because I don't have a lot of time, I will not talk about problems during analysis, but I will present you analytical method development and one study provided by GRS. There are some tools currently available to help and support researchers ensure that they are reporting enough details to guarantee high quality outputs and produce comparable data and harmonization. This includes sampling strategy, collection, preparation, analysis, quality assurance and quality control criteria, and data management protocols. Nowadays, there is a lack of reference materials, which is a huge problem for analytical laboratories. And reference materials are crucial for identifying appropriateness of methods, especially when accurate estimation or underestimation may occur for microplastics. To date, there have been several attempts to generate referent materials for microplastic studies, and these usually take the form of including a known number of plastical particles into a sample and counting their recovery. This method has limitations as particles are often more uniform in shape and larger than microparticles typically found in environmental samples. Furthermore, validation of reference materials is often lacking. More recently, researchers have been exploring cryomilling and sonification to achieve more environmentally relevant particle shapes and size range in recovery tests. As I said, GRS Joint Research Center, and in collaboration with German Federal Institute for Materials Research and Testing, organized an interlaboratory comparison study on how to measure microplastic in water. And this report provides an overview about an interlaboratory comparison study on microplastics in water and describes the technical details of the study, starting with the preparation, characterization of the PET-containing tests, items, and the study gives a comprehensive picture of current methods and procedures applied in the measurement of microplastic in water. 16 different analysis techniques were used in this study, but unfortunately no methods could be identified that systematically seems to give results more consistent with the indicative range of expected results than others. Furthermore, a great variety of experimental practices was applied, making it difficult to identify individual factors that significantly influence the measurement outcome. In the context of this study, laboratories applied, as I said, 16 different techniques for the analysis of the test items, and this figure shows the most used technique was FTR microscopy, followed by optical microscopy and Raman microscopy. Then a variety of filters were used by study participants, as can be seen from this figure. Out of 11 filter categories, 4 are completely or partially made of plastic materials. Then another result of this study is that labware employed by the participant laboratories were composed of a broad variety of materials, many of them being used only by 1 or 2 laboratories. 14 laboratories used fluorinated polymers, of which PTFE was most common. On this slide, you can see the materials for specific labware, and on figure 23, you can see that the glass and metal, mainly stainless steel, were used most often. As conclusion of this study is that we need harmonization and standardization. The results of this study highlighted the technical challenges in providing robust results for microplastic content, and the questions and ideas shared by the participants of this study highlighted the importance of interaction between standardization bodies and the various actors who develop methods, organize further studies, and develop reference material. Current mitigation strategies are shown on this slide, and I can say that it is necessary to strengthen regulatory measures to emphasize the importance of proper disposal and recycling of plastics. But I can say that the most important is to inform the public about the dangers of microplastics and promote sustainable alternatives. And from our side, we can give some recommendations, such as that we should use products made from natural materials, such as glass, paper, and wood, then to replace or eliminate, if we can, single-use plastic products. To participate in sorting, recycling, composing, and appropriately disposing waste. Then to optimize our shopping habits. Yes, it's very important. To seek out like-minded people who can guide us towards solutions, to understand our concern and provide encouragement, and to share our knowledge and experience like we are doing today. Thank you very much. I hope that I managed to tell you everything I wanted to for this 20 or 25 minutes. So if you have any questions, I'm here.
Thank you, Natasha. That was very interesting. There is some time for questions. If someone wants to raise their hand, and when Santa, you have raised a question in chat box, you can actually explain.
Yes, you said, Natasha, that it is necessary to develop like a standard methodology to find out what is the best methodology for analyzing these microplastics. Is there already a group working on that within a standardization body?
I know only about this study which I presented by Joint Research Center, and 100 laboratories were involved in this study. But I don't know, is there some group which is working on this standardization? We have a huge problem with standardization of analytical methods, as I said, and as you can see from my slides. Every laboratory uses different methodologies, from sampling to the instrumental analysis. So there are a huge, very big number of scientific papers, and they are all talk about their own methodology, but unfortunately, I can't say that any of that is a good methodology, because there is no standard methodology.
Thank you. Are there any other questions for Natasha? You can click on the reaction button and raise your hand, or you can use the chat box. Okay, so we are on time and we can move to the next presentation. Debolina from DigiTouch will present sustainable upcycling of plastics for circular economy and greener environment. Debolina, you can unmute your own microphone and you can start your presentation.
Can you hear me?
Yes, we can.
Okay, great. Maybe I share my screen. Just a minute. Can you see it? Hi,
We
Angela.
can't.
Okay. Now?
We can, I think it's blank. Yes, we can now. Thank you.
Perfect. Okay, and it's yeah.
It's in presentation mode. So
Yeah, and it's moving, I guess.
I don't know if you can click and see if it's moving.
Yeah.
Yes, yes, great.
Okay, finally. Okay. Hi, this is Evelina. Maybe I start my camera. Hi, this is Devolina. I'm a business developer and sustainability expert in DigiTouch. Today, I'm very grateful to be here. Thank you for giving me the opportunity to present our work. Moving on, when it comes to plastic, well, plastics have been adopted in a significant and ever-expanding range of products, thanks to their relatively low cost, ease of manufacturing, versatility, etc. Plastics are everywhere in products as simple as paper clips to as complex as automotive components or medical devices. But in reality, plastics are causing many problems in terms of waste and pollution. Most plastics are made from non-renewable sources and are not recyclable, reusable, or biodegradable. Therefore, addressing plastic waste is crucial for the greener environment as it reduces pollution, conserves resources, and minimizes harm to ecosystem. In fact, it is vital to mitigate the environmental impact that comes from plastic. Actually, a few days before, we just had a circular week. Basically, we are moving towards circular economy, which is an economic and environmental concept aimed at minimizing waste and optimizing resource utilization. Which is actually contrasting with the linear economy, which has a wasteful approach. In a circular economy, resources are constantly recycled, remanufactured, and reused, creating a closed loop system. When applied to plastics, this approach emphasizes designing products with recyclability in mind, promoting plastic recycling and upcycling to extend the lifespan of plastic materials. So the key principle remains here involving reducing single use of plastics and fostering the reuse and repair. So far, many solutions have been placed to get rid of plastic waste, such as mechanical and chemical processes. But mechanical recycling downgrades plastic properties, while chemical recycling requires high energy and long reaction times. On the other hand, bioplastics are the promising alternatives, but they're still expensive and not widely available. But what if we have an alternative exists? That is what we are aiming for. upPE-T is a novel upcycling process to transform PE and PET waste into bioplastics that is developing. Now, upcycling. We usually talk a lot about recycling, whereas upcycling is relatively new. well, it's not that new, but when we listen to upcycling, it's kind of new for many of the people. So basically, it's an innovative and sustainable method that involves reusing materials by transforming them into products or greater quality or value than the original state. In contrast to recycling, which actually breaks down materials into raw components, upcycling repurposes items with minimal energy and resource consumption. This approach promotes innovation, artistic expression, and environmental responsibility. The upPE-T project aims to turn plastic food and drinks packaging waste into a valuable resource for making PHVB bioplastics. To achieve this goal, we are working on developing biocatalyst degradation routes to break down the two most commonly used packaging plastics, which are PET and PE. The resulting products will be used in fermentation strategies to produce a PHVB bioplastic. Once these processes are scaled up, the PHVB will be compounded and turned into actual demonstrator packaging products. But while working on the upcyclability, we need to make sure, actually from the very beginning, we were sure about that. We wanted to do that, that the process is sustainable. I mean, to save the environment from plastic waste, we don't want to create another mess, right? We don't want to create a process that is not sustainable in terms of expense or GHG emission or social adaptation and so on. So we make sure that upPE-T process is not only environmentally, but also economically and socially sustainable. Therefore, we focus on LCSA, which is Life Cycle Sustainability Assessment. We probably all of us know about LCA, which is the life cycle assessment, but we have combined the three aspects to have an holistic approach, which is environmental, economic, and social aspect. So LCA, LCC, and SLCA assessment. For LCA, we follow ISO standards, and amongst all this, the most challenging phase we have so far encountered in this project, in fact, all the project that is common, is life cycle inventory. So first, setting up the goal, which is goal and scope, which shows us the path, and then comes the inventory part, then the analysis, then the assessment, and then the analysis. So the second phase, which is life cycle inventory phase, it's the most challenging phase, because during this LCI, we obtain data that can be primary data or secondary data. The methodology for LCI differs depending on the analysis we are doing. Data can be collected directly from the source or literature, or by using databases. So we are doing all three almost. Especially, we are trying to have all the data, all the primary data from lab, and thanks to all our partners, so those are actually giving us that. It's not easy to have very detailed data, but yeah, we are trying on that. Then we definitely adopt other databases and so on. And then, of course, the assessment is performing by us. We have different databases actually. EcoInvent has been chosen to support the LCA modeling. There is a plenty of databases in which many unit processes and flows are contained. The most famous and consistent is EcoInvent, according to us so far, which goal is to create a database in which many kind of processes are modeled to have more consistent LCAs. For all three, LCA, LCC, and SLCA, we have customized template for all the sub-processes because they're definitely not the same. The approach of SLCA is a bit different than the other two. the social approach, it's a bit different because there we had to identify the stakeholders, select the stakeholders, and everything we have been doing this following the UNEP methodologies and then selecting the indicators and follow them. upPE-T is an innovative project. For this reason, most of the processes, actually not most, now we have plenty of data, but many of the processes, let's say, are still ongoing or in the experimental phase to have a clear data collection. More to this, there is a scarcity of literature, both on the single processes or the process. Of course, the process itself doesn't even exist. So, which means it is not possible to use literature data in a large scale to perform LCA. Furthermore, while PHBV is currently utilized on an industrial basis for food packaging in upPE-T, it is obtained from upPE-T degradation in laboratory. So we have two types of lab data and industrial scale data. Collecting primary data on laboratory scale does not reveal a comprehensive sustainability indicator for an industrial scale processes. In other terms, we collected some data from the ground, but they're not definitive at times. They will change, of course, because this is science and this is experiment. This is research project, so they will change, and so the LCA. More even if the databases we choose, which is EcoInvent, help us to perform the LCA. Some of the unit processes are not available. We are building it, which means that, of course, we have to be modeled based on the data we have. So in our approach, we aimed to perform ex-ante or perspective LCA, where assumption plays a crucial role. So this is also kind of relatively new process, new concept, because LCA has been performed largely in industry, where the products or the processes, they're already established for a few years or years. Then you do have all the data, everything is scaled. But in the research projects, there is data scarcity. And now we have a lot of innovative projects like this, like chemical processing, upcycling, recycling. In fact, the IT projects, there are plenty of IT projects where people are creating data modeling, data stores and so on. And there is a need of checking if it is sustainable. So what to do in that case where there is no standard for this? So basically that's why when there is lack of availability of data, there is no quality data, there is uncertainty, there is no comparability, then ex-ante LCA is being performed, which means that we need to be modeled processes on the data we have, which imply to make assumption based on the fact that data sometimes are not complete. More to that, given that some processes are in the industrial scale in upPE-T and some others are in lab scale, we in this case, we needed to split the analysis at the beginning. So we will have one LCA based on lab data and one for industrial data. Maybe later on we will collaborate both of them. But yeah, so far this is the case. But we are talking about life cycle. So it may be natural to think that this kind of analysis has to be made at the end of the project, which makes sense. But we cannot get a comprehensive sustainability score while the processes are still ongoing. But given the iterative nature of LCA methodology, it is actually useful to perform the LCA from the primary stages. That is what we are doing. It is complex to start the life cycle assessment or the life cycle costing assessment, all of this at the very beginning when there is no data. But it is, on the other hand, helpful. First of all, we do have an estimation of the impacts, that what can come we also have the idea of hotspot, and by comparing with existing system, we know if our solution is good or not. Not only the LCA helps to identify the hotspots in the process, but it can be mitigated through valorization. And that's what we are doing in upPE-T. We do have valorization process merged with LCA, the sustainability assessment. So some of the hotspot can be reusing water or using enzymes throughout the process. And that is not only help to reduce the usage of the resource, but also reduce impact emissions. On a different note, further to that, in upPE-T, we do have certification schemes also integrated in the process. So the Cradle to Gate certification, that is a leading certification, standard used, very much standard used by globally across industries by designers, brands, manufacturers for designing and making products that enable healthy, equitable, and sustainable future. So yeah, that's more or less it from my side. And here I conclude my words. Yeah.
Thank you, Debolina. Another question from Santa again.
Just a
Well,
minute.
my question is, through life cycle assessment, we are like assessing the environmental impact of processes or products. Is the potential release of microplastics addressed in life cycle assessment?
Here in upPE-T?
In upPE-T or in general, in the methodology of
course,
life cycle?
of course it is.
It is, okay.
And that's why we are doing actually very refined analysis to get all the components that we can get, part by part, through all the sub-processes.
Okay.
Okay. Another question for following. So Valentina.
Yes, hi Debolina. Thank you very much for your presentation. I'm also working with life cycle sustainability assessment in the sister project Uplift. And my presentation will be very similar to yours. I just wanted to ask you, how far are you in the project and how do you think you're doing with respect to data coverage and processes modeling? Because that's our biggest obstacle.
Challenge.
Yes.
Yeah.
So I developed, for example, prospective LCA methods. But
Yeah.
even though you have the methods, it's also very hard to have the starting point. So I wanted to ask you how you're doing that.
Yeah, indeed. That's why I actually highlighted this point of LCI, which is the data collection method. So we are in almost last phase in the project. But of course, we had a lot of challenges to collect data. We are still working on data collection. But what I would say, what we did is we separately go to the partners, and we often do it because in the research project, a lot of things change. Some processes don't work, some processes change, some processes, some other alternatives come all of a sudden, and we do not have any idea what is going on so, from this part. So what we do, we time to time meet the stakeholders, and we do have all customized templates or data collection methods for all the sub-processes. This is one. Second is we try to update them because they are also going from lab scale to from lab scale to let's say scaling method. So then the data changes. So we also try to collect that. And if the data is not absolutely available or some models are not available, then we try to look at the commercial databases if some models are available.
Yes,
So that is also we are doing. And as I think I already mentioned that initially we had difficulties because some were lab scale and some were industrial. So we had a meeting and we split the analysis. So we had one lab scale and one industrial scale, but later we will probably collaborate both of them. So this is for LCA. Actually, we are trying to do. It's very challenging. I know you probably know it already. So
yes, yes. Well, I will be in touch and looking forward to seeing your study.
yeah, thank you very much. Yeah.
Thank you very much.
Thank you, Valentina. Are there any questions following the Bolina's presentation? I can't see any hands rising. If you have any questions, just click on the reactions button and raise your hand. We'll give some seconds if someone wants to ask anything. No? Okay, now.
Sorry, Angela, you didn't
Yes,
see I raised hand, yes. Debolina, thank you very much for your presentation. And I want to say that we also bought LCA software in our Greenland project, and we are just starting to use it. We haven't used it for microplastics so far, so it will would be very useful for us to get some suggestions from you, since you have more experience. So this was very helpful for me to get some ideas. But if you're interested, we can arrange some maybe a meeting or a Zoom meeting to ask you some questions for LCA using for microplastics.
Definitely. Which one did you buy?
Gabby.
Gabby?
Yes, Gabby.
Okay.
Gabby.
Okay. Yeah, when you said bought, so I thought it must be Gabby. Okay. Yeah, sure. We are actually using OpenLCA databases. We bought the database, but we for the software we are using open source. So OpenLCA and Gabby, they are not very far, little bit close by. So yeah, sure. I think methodologies and stuff, they are kind of similar. So yeah, sure, we can have meeting further. In fact, we have another member in our team, which is she's more expert, in fact, particularly in LCA. So we can have meetings.
Thank you very much. I will be free to contact you after this meeting. Thank you.
Thank you.
Thanks, Natasha. So the collaboration is ongoing. So are there any questions before we take a 10-minute break? And no? So please stay tuned. We have 4 more presentations after the break. So let's have a 10-minute break. No, 7-minute break up until 10 past 11. And then we will be back with Ines from Boku University. Yeah? See you in 10 minutes. So it's 10 past 11, so we can continue with our agenda. Ines Fritz will do the presentation now about how microbial communities use polymers as substrate. So Ines, over to you.
Okay. Hello and welcome to my presentation. Thank you, Angela, for introduction and the organizers for making this webinar possible. I like to start with admitting that working over 40 years in microbiology has somehow changed also my mind, and I like it a lot to destroy products other people have hardcore produced. The same as microbes are doing when they are using a substrate like a polymer for their living operations. We are talking about microbes, and we are talking about how they degrade polymers. That means they need to be biologically active. They need to be alive and active, metabolic active. And they need the usual things you all know: water, carbon source, energy source, oxygen or no oxygen, minerals, trace elements, and so on and so on. And as the tree of life here schematically shows, especially microbes have a very, very wide range of metabolic activity, and also have, therefore, also a very, very wide range of possible environmental conditions, substrates, minerals, temperature, and so on needs. And this wide variety usually leads to the situation that almost everything that you can find in the biosphere of our planet is somehow usable by a microbe. So what is then a suitable substrate? It is something that delivers energy and or elements, mainly carbon, but also nitrogen, phosphorus, potassium, and so on, and preferably delivers everything of it. And this something can be assimilated as such or after a transformation, for example, the cleavage of a polymer into monomers. And now the question, the next logical question is, how do microbes know about a substrate is in their range, in their reach? How do they know about the presence? So they cannot look, they cannot smell. Oh, yes, they can smell, but they cannot hear or otherwise recognize if, let's say, 3 meters away from their position, something delicate is waiting to be degraded or used as substrate. So the usual thing is all the microbes release constitutively some extracellular enzymes which are able to cleave, let's say, the usual polymers, the usual substrates they can find in their environment. So these are hydrolases, proteinases, oxygenases, some things that can cleave bigger molecules into smaller. And the smaller then will be released by the permanently present enzymes in the environment and will diffuse back to the cell, and this then causes a signal that the microbe then will start targeted for which molecule comes back, the responsible enzymes, to get more of it. And that's the start of a biodegradation. That's the start of the recognition of a microbe that there is something to be digested. But there, one question remains. What is the difference between there is no substrate or there is something there that cannot be accessed by the enzymes? In both cases, no signal will come back and the microbe will not trigger its metabolic activity, and therefore nothing, when we look from outside, will happen. So, but what happens if there are multiple substrates there around? Let's say polymers, monomers, more or less interesting substances, more or less interesting in the same sense that they provide energy, carbon, and so on and so on. The best comparison is what you see in the image there, the comparison with an all-you-can-eat buffet. I always tell to my students that the next time they join such a buffet, they are not allowed to pick anything. They have to stand aside and watch other people's, how they are operating. And the usual is, and that's not a surprise, that the most interesting, and that's different from one human to the next, that the most interesting pieces will be picked at first, the second interesting second, the third interesting, and so on. And you can follow. And if we reach the, let's say, the 30th variant, this will be on the 30th place, most probably. And then you have to ask yourself, and when, at which time, people start to pick the decoration or the textiles on the table or the table itself, And we can answer very quickly, never. Never ever, at least not as long as there is anything else which tastes or which appears to taste better than the decoration or the textiles there. So usually we have a row of an order of most preferred to at least preferred substances to be utilized. And you can already imagine that there may be a problem when we talk about plastics. So currently and generally spoken, all substances produced from organisms, and I mean by biochemistry, by metabolic activity, will become biodegraded sooner or later if temperature, water, oxygen, and so on, all the other conditions are favorable for supporting the microbial activity. The biodegradation is therefore the base for the big global nutrient cycles. This is good for life and evolution on Earth, but this is bad for human living and for materials and products which are intended for a prolonged life span. So the usual thing which we as a human society declare as a problem is that the natural materials somehow decay. They will be degraded, mold will grow on them, and so on. So they have a natural, limited lifespan. So the first solution, which happened in the early 1920s, 30s around, was to invent macromolecules with the specific target and goal that these molecules can resist the microbial attack. So if the constitutively released enzymes from the microbes will hit such a polymer, no signal will come back. So the microbe will never recognize that there is something, and therefore it will not be degraded. That's the thing. Then from this, another problem arose, and that was that these invulnerable products will destroy the business, as you sell everything once, and then it will stay there forever until I think the sun explodes. And therefore a new solution was required, and this was the planned obsolescence, and with the peak, the top of the invention was single-use products. So therefore, as a producer, from the point of view of a producer, you can be assured that the moment you produce something, it is already waste and you can produce it again. That's ideal. However, there a new problem arises, because then we have suddenly a waste that is persistent, and then the waste will, as a material that doesn't biodegrade, will persist there for every time until end of all times when the sun explodes. And therefore we are now seeking for a third solution, and that we call biodegradable or non-persistent plastics, to somehow keep our usual, let's say, behavior without the follow-up problems. But to be honest, if we think about a bit deeper, which problem do we solve? Which problem we did not have when you go back to the first line, that natural materials decay, and biodegradable materials, biodegradable plastics is no different. So also this will decay. So what exactly is the difference? I will not give you an answer now. This is your homework. Please consider. And there we are with the problem, which is visible, which is in all media, and you can make your own image search on whichever searching machines you like to do. What is less common known is that we have a similar, if not a bigger problem in our soils. And there is, I would say, end of fun, because when we spoil the sea, we may tell, okay, I can fish it out again. We know nobody will do it, but we can technically, principally possible. But the plastics we release in the soil will stay there forever, and you will already know what comes now until the sun explodes, and there it will stay. Remember the all-you-can-eat buffet. If you have such soils there is organics there are minerals, there are microbes there, and there are plastic residues, easy to identify in the visible light microscope. So which priority, which interest will they have for the microbes? It is zero, because they will not produce any signaling from the constitutive released enzymes from the microbes. So this problem we have already, we are facing now, and it should be our responsibility to make it not even bigger than it is already. But that wouldn't have happened if the plastic would not have been released into the environment. Okay, but this already happened, and it goes on with non-decelerated speed. The released plastic would have been fully biodegradable in foreseeable time. This is also something to mention together in the environment in where they landed. So again, the second homework for you, which of these causes can we and which should we change? The one or the other? Do we look for a technical solution for a social problem maybe? So what are the possible answers here? For option one, not spoiling the environment, we can make a global production prohibition. I think, yes, that's a nice joke. Or we can have a 100% collection and treatment order. This is something we are on the way, but currently Europe is at 6%. So we have 94% more to go. Or a permanent observation and sanctions for intentional dumping and losing. So each of us needs a shadow person watching us the whole day. Okay, the next joke here. Or we replace persistent with non-persistent materials in the intention that we the humans, part of our society, do not need to change our behavior. So, okay, that's also very interesting. Or the option two, remove the plastic and microplastic from the environment. But I have told you already that is next to impossible. Imagine only how to pick sub-millimeter particles in size from soil, from square kilometers of soil surface. No. So let's then talk about the most promising of all these options, and that is use of non-persistent plastic. We also can replace this word with use natural-like materials. Yeah, that's I think the way to go. So what is degradable? Degradable or degradation is the change of the chemical structure. So a substance A, like a polymer, becomes a substance B, like a monomer of this polymer. So chemically different. Biodegradable is this substance if this chemical change is caused by the action of an organism. Disintegration, in contrast to this, is something very different. This is a loss of physical shape and structure, but doesn't need a chemical modification. If you know already polyvinyl alcohol, for example, PVA, this is water soluble. So the visuals, the appearance of such a product changes dramatically as it is dissolved in water, but it is not biodegraded. This is something very often, quite frequently, is mismatched, that degradation and disintegration are two very separate happenings to a material. And something organically recoverable, and I think that's what we all have in mind when we shortcut what is the meaning of it by only calling it's degradable. So that's the common language to say it's degradable. But what we usually mean, it should be organically recoverable. And that's a material or a product that can be collected and treated as if it was a typical organic waste. The same as the banana peel or the residuals of the onion or whatever in food and green leaves or whatever. So there are prerequisites when this material should behave the same way as the usual bio-waste, organic waste. It does not allowed to contain harmful substances. It should be biodegrade in due time. It should disintegrate in due time, and it should not disturb the treatment process itself and should not somehow modify the quality of the resulting compost. And exactly these four requirements are covered in one of the older European standards, the EN 13432, which was released in 2001 originally, and they are released with the intention to make a test scheme and to make requirements that exactly analyze and claim that these four requirements are fulfilled, all four of them, and if they are, then marking as a compostable or biodegradable, together with the organic waste, collectible and treatable material is there. So we have that, we have the design, we have the biodegradability, we have the material disintegration, and we have the test of compost quality and ecotoxicity. This looks something like that. The left two photos there, at the most left is an aquatic test, continuously steered, where you can make something like a bit idealized environment, where you do not need to analyze some inhomogeneities in your environment. In the middle, you have a test for a solid matrix. In this case, it was a soil matrix, where there are already inhomogeneities happening in this type of test, and the rest is not the right side is not a quantitative test. This was an oriented test where you go into direction disintegration in an applied environment, in this case plant pots in a greenhouse, for example. So I have brought to you an example from the praxis why it can be useful to use biodegradable and compostable plastics, for example, for food packaging, because usually this food packaging may be discarded into the organic waste bin if you have a source separated waste collection with, let's say, a spoiled content, with a spoiled food content that is not longer edible. So there we have this reduction of plastic waste in the organic waste bin. We have therefore also an increased amount of compost because this is not sorted out, or it is also not thrown into the residual waste bin, and therefore the organics is lost. And as a side effect of this, very interesting and a bit surprised was that it is already proven that food packed in such a material with such properties increases the shelf life of fresh food. The thing is, the limitation is to fresh food, something we also in upPE-T are addressing and will be analyzing soon. On the long term, there is some indirect education of people, and that's usually the thing, and Debolina has already mentioned it before, thank you for that, that those materials are comparably expensive. We can see it as a disadvantage, but I am sure I like to guide you to see the advantage of the high price, and that is the high price product will not be thrown away so easily, so mindlessly, as something that is so cheap that you or the people out there will not recognize that this is associated with cost. So if this packaging has some cost, it will be much harder to throw it out of your car window during your drive through the landscape. However, what we have to beware of and what we have to address is to fight against laziness or corrupted understanding of wealth. And we cannot delegate the responsibility for a certain, let's say, beneficial behavior to the public if we do not tell them what is the consequence of doing the one or doing the other. That's something we have to keep in mind. This is only remembering because this is very old news. Already in 1994, European Parliament has decided that there is a priority, and that is not only for, let's say, fossil-based conventional plastic, that's also valid for new materials, that if you produce something, generally you should avoid the material. But if it's not possible, then you should design it for reuse without any mechanical intervention. If that's also not possible, then you should design it for recycling. And even if that's not possible, then the last option available, and that's really the fourth and last option there in the priority list, is the recovery, either by energetic or by organic recovery. So when we talk about the production of biodegradable plastic, we are not talking about to replace substance A with substance B, make a mass production, and do not care any longer. So that's my emphasis to you, to think about and to be sure about and to know about these priorities which have a background in environmental protection. So please continue to think about your understanding of wealth and consume, and thank you very much for being here.
Thank you, Ines. So now there is the opportunity to raise any questions following Ines' presentation. We still have a few minutes before the next presentation.
I was too quick, huh? Okay. Okay.
You were too quick, yeah, but it was very content and
Okay.
interesting, the presentation. Are there any questions for Ines?
I think the questions are for the public, for our listeners. Yeah. Okay. So,
Yeah,
so please take your homework.
Yeah.
Okay.
Okay, so
Okay, thank you. Yeah.
there is the opportunity. Thank you, Ines. There is the opportunity also at the end of all presentations for participants to raise any questions that they may have. So let's move on to the next presentation from Valentina Bessinella from the upPE-T project. Valentina?
Hi, hello everybody. Can you hear me?
Yes.
Good. And now you should also be able to see my presentation, I guess. All right. So, yes. So I was here today asked to present our activity in the upPE-T project, which stands for Sustainable Plastics for Food and Drinks Packaging Industry. We are a very big group. So as I said, I'm very honored to be here presenting the project. Our work is in the sustainability assessment package, and that's why I'm here today. I am an associate professor at the Technical University of Denmark, and my background expertise is on life cycle assessment and prospective LCA, so the topics that were addressed earlier by Debolina. So what are we gonna look at together is a little bit of a background on the upPE-T project and on what sustainability assessment is to us. We already saw some introduction from Debolina, and I will talk about what we mean by sustainability assessment and sustainability within upPE-T. And I also have some take-home messages for our listeners. So the upPE-T project is a project that aims to tap in the value chain of plastic products And the reasons are those that were presented by the other speakers before me. It's about this mining of primary resources that's not stopping, and the need to at least trying to close loops in our consumption patterns and value chains of products. So what is this project looking into? You can see it here at the left of the screen. Because plastic recycling can look into closed loop and open loop recycling, while the ambition of this project is to go from collection and sorting of plastic material and plastic waste to enter a biochemical recycling loop that aims to introduce new ecopolymers in our value chain, easier to recycle, and it aims to go from lab to pilot scale. So how is this going to work? So first of all, this aims to start from plastic waste and to go straight into monomers and polymers. So it should be able to accommodate both different materials, but also be able to provide new materials. So how is the project going to work? So we want to apply novel biochemical upcycling technology routes. So this means designing bioplastics that are recyclable or biodegradable, develop new biotechnologies based on enzymes and enzymes combinations and microorganisms for improved recycling or biodegradation of plastic. So I will talk a little bit more into this in a minute. And the aim, as I said, is to develop a more sustainable plastic packaging value chain. And this value chain is especially targeting the food and drink sector. So in order for this project and this product to happen, we not only have to prove the feasibility of these products from a lab point of view and sustainability point of view, but also that this is potentially a solution that can find ways to be used. So we need novel standards and certification schemes, and we need to make sure that we include all the stakeholders. So for example, social acceptance, and of course, involving a systemic approach. So for all actors in the supply chain. And these actors in the supply chain are well represented in the project because we are a big group of many scientists and researchers, and as well as experts of polymers and pilot producers. So how does this work? It's represented in this cycle. The overall concept is to start from traditional plastic waste, and this can be more or less complex. I will explain better about this complexity. But we start from traditional plastic entering the waste management system. And these plastic polymers will go into enzymatic and microbial depolymerization. From this depolymerization, we will obtain some hydrolysates, which are then going to be used after purification in the production of some monomers. And the ambition of the project is to produce these monomers starting from the hydrolysates, but also including bio-based feedstock. So then the polymerization process into ecopolymers will integrate the biological upcycling within already existing processes to large volumes. And then the formulation would then help having some ecoplastics, which are then redesigned in the food and drinking packaging value chain, introducing these chemoenzymatic recycling and eco-design materials. And the ambition is that this can enter the value chain and compensate our need for virgin sources of for our production of plastics. The entire concept is backing up the transition of plastic packaging sector because we have goals for 2030. And the expected impact and the context of this process was well explained by speakers before me, but 60% of food and drinking packaging is aimed to be upcycled by 2030. And we should be able to reach, according to EU targets, that 60% of our plastic used for packaging is produced from renewable sources. So new and upgraded waste recycling facilities need to facilitate recycling via biotechnological or biochemical methods. And we also need these novel standards and certification schemes to be applied together in order to make sure that the market is ready, not only from a technical point of view, but also as a regulation, and the entire value chain can accommodate this. As I said before, it takes a village in order to accommodate this project. So we are many partners, 15 partners, subdivided in 8 work packages, and for a 4-year collaborative project. We are involved in the sustainability assessment, so eco-polymer design, but also the assessment of the entire project and value chain. We have partners that are waste management companies. For example, you see Vespa Bratning is a waste management company in Copenhagen, Denmark. We have many partners working on depolymerization of materials. As Debolina was explaining very well earlier, many paths are actually explored. So all our partners have been investigating many different depolymerization techniques and microbial consortia and enzymes and so on, as well as the partners for the fermentation part. We also have ecopolymer design, but also production. So it takes a lot of partners in order to reach this goal. I was asked to talk today because I am involved in the sustainability assessment package. So I will talk a little bit more about sustainability now. So what is sustainable? Sustainable, as you can see in this slide, actually encompasses many different aspects. Economy, regulation, health risk, environmental impact, materials use, acceptance, and resilience and flexibility. So there are many different aspects that need to be taken into account when we look into sustainability. And of course, we can break them down into economic, environmental, and social, but what do we mean there? Sustainability assessment is a concept that started in the 1980s, and it's still playing a very big role in our European vision for 2050. We want to live well within the limits of our planet, so we can also look at global targets, for example, the United Nations Sustainable Development Goals. When we talk about sustainability, we have to look into multidimensional approaches, and we have to take into account all the aspects that can play into this sustainability. When we want to have a sustainable transition, so for example, in the case of Uplift, we want to go from plastic waste to new bioenzymatic processes, and we want to have a new material that can enter the value chain for food and drink packaging. We are talking into a sustainable transition, so a considerable shift in one of our value chains in our society. And what the the European Union suggests is that when we look at these fundamental systemic changes, we need to have knowledge as one of the enablers. And in our case, we use life cycle assessment as a tool to rehearse change. So it's a model setting. And although conditions in this model may be very uncertain, from managing to obtain data or how to handle the primary data, database, and literature data dilemma, is still very relevant because we will produce some knowledge, and this knowledge is one of the enablers of this transition. So we use sustainability assessment models, and we aim to use these models as early as the research and development phase, because we want for technology development, new materials, new products, new supply chains, to assess what are the potential impacts that we can already envision. We want to assess the potential benefits and identify drawbacks and hotspots that can allow us to reach as much sustainability indicators as possible. So in the same case as the upPE-T project that was presented before, we use life cycle assessment. So I don't have to repeat a lot more than what was already said. Life cycle assessment is a standardized procedure, and it is particularly interesting in this knowledge enabling process because it allows us to have a systematical approach to assess potential benefits and drawbacks for novel products and systems. We can look at environmental, economic, and social aspects, and it allows us to understand the system in terms of inputs and outputs. For example, how many chemicals are needed for a specific step of the process? What are the yields of these depolymerization? What are the wastes and how much energy do we need? And we can relate this input, which is the life cycle inventory process, to potential environmental impacts, costs, and aspects. So we will have a systematic overview, but not only of the single steps of the process, but also of the entire supply chain. And I will explain a little bit better what I mean about that, about systematic overview. There are different procedures and software available. We talked a little bit about EcoInvent. We talked about OpenLCA and Gabi in the previous presentation. We use a model called ISTEC, which we develop at DTU. ISTEC is an input-specific model which follows the mass flows and the substances in the system. So basically, for the man on the street, it's not only kilos, but it is kilos of a specific type of polymer with specific physical-chemical characteristics. So we aim to link these characteristics to our bottom-up model of technologies. ISTEC has been used in the research group where I work for over 20 years, and it is specific for waste management. So that's why we enter the project, because uplift starts from waste. And so how did we do it? So here I opened up about our procedure. So if you remember before, uplift was a circle. So in order to carry out a sustainability assessment, or to try to start to carry out a sustainability assessment, we have to open up the process into its basic steps, which I have shown here. We have the traditional plastic. If you remember, the boxes are the stages, and the drawings are for the products that we have. We have enzymatic depolymerization, bioupcycling and purification, polymerization and formulation. So for each of the steps on the way, we define inputs and outputs. This is what Devolina was telling you about. It's life cycle inventory, amounts and composition. And for each step, we need chemicals, energy, enzymes, and we will produce some residues, some water on top of our products. So this is the part that for us was the most challenging, because as it was said before, processes evolve. For each work package, for example, I give an example of depolymerization, we may have different experiments carried out. So it's very hard to foresee which one is going to be the one that's going to be chosen for the next phases. And for each one of these, we have the challenge of going from the lab scale to the potential pilot scale. The need for chemicals and energy and enzymes are going to be different at the pilot and from the lab scale. But also it is very hard for our partners to help us with data if they're not LCA specialists. And that's why we talked about the need to to meet with them and to ask them many times and update them on the process. So this is, for example, what we talked about before, and this may be a little bit new, I don't know. But what we also do is expanding the system boundaries to the current management of the traditional plastic. And this is because, of course, we can evaluate a new value chain and a new process. But in order to, when we do a life cycle assessment, we will obtain some results. But in order to say whether this is much better or much worse than what we do already, we have to compare this to the status quo. So part of our work is equally important, looking into how mixed plastic waste is traditionally treated, which means mechanical recycling and low purity plastic recycling. And with upLIFT, we want to look at mixed plastics and also plastic films, because recycling, mechanical recycling of high purity plastic may already be well established. So our goal is to look into this system and in the same way, determining amounts, compositions, chemicals, and energy in order to have a benchmark for upLIFT. So in our life cycle assessment, of course, we are going to have uncertainty, and we cannot solve the problem reaching a very precise number of sustainability assessment. I will go back to that. But at least we can say how much better do we need to be with respect to the benchmark. So for the overall assessment, when we talk about environmental, economic, and social assessment, we are not only looking at our new chain, but we always have to keep in mind what is the status quo and the benchmarks. And in order to do that, even though we have very uncertain data, or we have data that comes from literature and databases, we can identify benefits and drawbacks, hotspots, and what are ranges where we need to be in order to potentially have a better performance. I don't have results because we are still in the process of compiling our life cycle inventories. But our status is, of course, a good understanding of current mixed plastic waste management. This data comes from our experience in the field, and we have a lot of data coming from literature on mechanical recycling, for example. So where are we for upLIFT? At the moment, there are many experiments carried out by our project partners on single polymers. This means, for example, pure PET and pure streams. And in this status, lab scale is still difficult to introduce in the model, and we do need information on the scaling up. And we are working on separate processes at the moment, but we know that we will need to update the model again. Lifecycle assessment is iterative to have better data from the project partners, but also hopefully going towards mixed plastic more than pure streams. The biggest question, which was also introduced before, is how can we model a system that doesn't exist yet? And how can we use data from lab scale to help the research and development process? So our suggestions and future work, and this is the end of my presentation, is we advise other practitioners that are listening today to start from the current system understanding, because this is going to be the benchmark in terms of environmental, economic, and social assessment. And the current system understanding doesn't need to be super in-depth study, but it allows us to have at least a range of potential environmental drawbacks, economic and social drawbacks that we want to be away from and change. So we will reveal an approximate range of impacts that the new solution needs to reach or provide a better performance on. And for the new technology, we know that as good as possible early screening allows identifying data needs. So which data, but also the units. And in order to do that, we can use data from literature. And by literature, I mean scientific publications, because at least we can identify which data needs and units we need. And this is something of the work we have done to identify units to send out to questionnaires to the project partners. So how far is the screening from the benchmark? How many orders of magnitude are we higher, lower, or similar? Early data helps other project partners helping you with data gathering. And this is difficult to walk the talk. So it's very easy for me to give you this advice, but also I know very hard to do in practice. And it's being quite challenging for us because, as Debolina said, you need to meet the partners, give them templates, but also contact them and try to meet or call in order to get data. This is still our bottleneck. Sometimes there is no data at all. So what we are going to do in our next steps is to use, try to use ranges from what we have gathered instead of single numbers. We use the ranges based on literature data. We can also use proxies. For example, if there's literature data on the production of enzymes, but this might be a bad example because there's not so much literature data, or catalysts, similar processes, we can use proxies. And having some ranges at least tells us where more or less we can expect being in terms of environmental impacts. And then getting better data will asymptotically narrow this range. This is my advice. Of course, there can be different options, and it can be difficult to identify which is the winning horse, let's say. So not only you could use ranges, but also you could use different scenarios. And by scenarios, I mean copies of your model that allow you to include different options in order to also check whether different options would bring you far away from the benchmark or would more or less be in the same range. So this is my advice to you coming from previous studies and my experience in prospective LCA. I would like to say that it takes a village also for sustainability assessment, and that this work is not done by me alone. We have a postdoc, Ashkan, who's also present at the meeting, and I'm collaborating also with the associate professors, Anna Stamkort. And we are the sustainability assessment team doing the LCA work. We have also another working packages working on the social assessment and techno-economic assessment. And if you are interested in knowing what the project is achieving and doing, you can follow us in our social media channels. Thank you very much for listening.
Thank you very much, Valentina, for your very interesting and extensive presentation. Quite a lot of issues were raised. I don't know if there are any questions for Valentina at this stage. Debolina, yes.
Yes, thank you, Valentina, for your presentation. It's very interesting, actually. I just have one question. Since all these are innovative projects, UPLIFT, upPE-T, so what is your benchmark, like, or the competitive scenarios where you can show that your process is better than the existing ones, or some benchmark or some baseline? Yeah, how we are doing?
Yes, thank you, Debolina. This is very interesting question because, of course, in a value chain, you may have many different processes. So, of course, for example, the depolymerization processes show you can benchmark the depolymerization against each other. And this is what, for example, the other project partners are doing because they are lab experiment experts. And then they are at the moment selecting which process is most successful in terms of yields. When I was talking about the benchmark, is about the material itself that is going into the uplift cycle, which is mixed plastic, ideally. And your question is perfect, because I didn't say that the aim of uplift is to target the plastic material, plastic waste, that is not easily recyclable today with current methods. And this is not pure PET or hard plastic in general, but this is more mixed plastic that cannot be easily recyclable, and plastic films. So, so ideally, we should be able to find a way to treat this material, this waste part. And this is what we have a model for the benchmark. If, for example, we wanted to see how the process was better for pure PET, then we would look into pure PET waste alone. So it's really a matter of what material do we treat and do we aim to treat, and what happens to this material today.
And all from literature data, right? Mostly.
Yes, we are actually in a very lucky position, because we have worked with waste management, life cycle assessment, and processes for more than 20 years in my research group. So our literature data is actually first-hand data in processes and waste management. The waste we are looking at for uplift has been sampled in Copenhagen, Denmark, and it is mixed plastics that are source segregated. So we have data on the composition of those, the material, but also physical-chemical composition. And then we start from there.
Okay, great. Since we are in the sister project environment, so what I would just say, maybe we can have separate meeting later on. If the few data we can also have for our benchmark. We are doing also some benchmarking for upPE-T, but if some data you already have and those are not confidential, then we can use them and we can have it as our competitive analysis or comparative scenario. So we can have a separate call on that. If you
of course. And you can also meet Ashkan is the postdoc working on uplift, and he's also present here. And I think he would be very happy to talk to you and hear what your project has achieved, because we have the opposite problem of making sure that our partners help us with data, where it seems like you have been very successful, or at least try to be successful, because I know it's very hard.
try, because there are a lot of sub processes, and we try with our partners.
Of course.
Thank you.
But definitely. Thank you very much.
Thanks to Bolin and Valentina. Any more questions from participants?
I wanted to add that, as I said in the introduction, there are several topics with synergies between partners. Within the cluster of sister projects, we created a working group for standardization, another one for communication and citizen awareness, and the other one was for policy brief. So we can think of creating one for life cycle assessment, if we think it could be useful for all parts. Okay, so think about it.
I would love
we can
that.
discuss it in the next meeting for the sister project cluster. Okay.
Yes. Please contact us.
Yes.
We would be very happy.
Fine.
Thank you.
So yes, so instead of having separate meetings or exchanging emails, a working group can be set up around this topic. Thanks, Santa. Any other comments or questions for Valentina? we're doing very well with the schedule. So we are actually 15 minutes ahead in our program. So we can take our 10-minute break now, and then we can also meet again for the final presentation and the concluding remarks. Yeah, so I'll see you in 1/4 past. Stay tuned. We can continue our webinar with the last presentation from Teresa Calvo from Iten, Spain. Teresa, over to you. You are muted, so if you can, thank you.
Now, yeah, okay. Sorry. Well, good morning, everyone, and thank you, first of all, for inviting me here to participate in this webinar. So, well, here is my presentation where I want to explain specifically one of the developments that we are working in the Preserve project. Specifically, is the use of finished coating to reduce microplastics from recycled textiles. A little bit from myself, I work as project manager in Itene, and I belong to the materials division here in Itene. So, well, let's start with the presentation. This is the overview of it. First of all, I want to introduce the Preserve project, the European project that now is in the month 35 from 48 months that has the project. After that, I want to explain a little bit also who are we in Itene, this research center, and also our role in this specific project with also a huge consortium of partners. And after that, I will move for the specific development, as I said before, of finished coatings to study the reduction of microplastics coming from the nonwovens. And as last part, I will give some remarks of our current initial scaling up of the development and the initial manufacturing of the demonstrators to validate the development in Preserve. So, well, first of all, just to give some summary or the main goals of Preserve project, as you can see in the scheme, the idea is to obtain or to synthesize new biopolymers, also taking into account different technologies or trends in the challenging of developing new materials, such as, for example, PHA coatings, also barrier coatings based on proteins, and also using the densimation. And in parallel also, the idea is to study the different routes of the end of life of these materials, also taking into account technologies or specific processes such as enzymatic recycling or delamination procedures, in order to guarantee closing the loop of the using of these new biopolymers as packaging materials. Also, the idea is also to study other type of applications, not only packaging, that, for example, composites and also textiles. So at the end, the idea is to enhance the bio-based properties of these biopolymers in order to increase their use and their applications. Also develop upcycling methodologies or procedures in order to guarantee the circular economy, as I said before. And in parallel, even to develop novel standards or certification schemes for these new packaging materials. In Preserve, as I said before, we work together with other partners in the different value chain along the value chain of the materials, from research and development centers as ITEN or, for example, INPLAS, other type of more academic profiles such as University of Bologna or also ASU. And we are very lucky also to have important actors in the new packaging materials manufacturing, such as Sudpack or Bostik, and even end users that give us very valuable information regarding the actual benchmark and how we can improve the use of biopolymers, the new biopolymers that we want to develop, such as Janon or Ferrero in the consortium. So, well, inside Preserve, ITENE also participate, as I said before, and then now I want to explain a little bit how is our work in our main activities and our specific role in Preserve. ITENE is the Packaging Transport and Logistics Research Center. We are located in Valencia, in Spain, and we are more than 180 professionals working mainly in R&D activities with companies and in the different collaborative projects with other R&D institutes or universities. At the end, we are more than 60% of people also with a specific master's degree or doctorate in specific technical fields. Just to have an overview, this is our 4 main areas in order to transfer knowledge to companies and to increase the competitiveness of them. One of them is the materials and technologies for the circular economy, where Preserve is focused on this part, with the idea to develop new materials or to increase or to improve procedures to guarantee better end of life of materials and all this kind of activities. Other research area in the institute is the packaging safety, design and functionality, very focused on simulating the transport of goods, all the packaged goods, and in order to give the optimal conditions of packaging, of transport, the type of transport, and also the load in each of transports. Other part that also is involved in Preserve is the safety and environmental monitoring technologies. We have a division regarding all this part in order to guarantee the safety of the new products and also to guarantee and to study the health and risk of the common activities in packaging, development new materials or other industrial activities. And the 4th main area is the transport and logistics, where we also have are been working in order to increase the sustainability also in this part. So, well, specifically, ITENE Preserve work in these 4 main areas. The area which involves a specific development or a more experimental practice is the use of finished coatings to reduce microplastic release from nonwovens. But also we work in a transversal way with all the partners and all the developments in 3 main areas. Food safety analysis for all these new materials that are intended to use for food and drinks packaging. And also a safe design approach. As I mentioned before, we have a specific area in ITENE which works in all these activities. And the idea in Preserve is to guarantee the safe by design of all the new materials and products that are using now for developing the main demonstrators which are proposed in the project. And the last part, and not even less important, is the evaluation of circularity. Our role here is we are defining a methodology with an specific indicators in order to evaluate or quantify or even in a qualitative way the different routes that the new development of biopolymers and the new packaging materials are using during preserve development. So the idea is to evaluate how circular is all of these demonstrators in order to guarantee also the best ways with the new developments. Well, now I want to move to the specific work in terms of the finished coatings that we have tested in order to reduce microplastics. First of all, I want to, well, only to give some remember, because in some of the presentation also gave some figures just to make some figures of the problem of microplastics. It's true that the main source quantify is from automotive tires, but it's true that, for example, other typical goods that we have in our daily lives, such as a textile or synthetic fibers from clothing, is also one of the sources of the microplastics, which were quantified in more than 800,000 of tons from the European countries. And well, everybody knows the huge concern about that, and the idea is to give some solutions, alternatives, or approaches from the different fields in order to tackle with this problem. Also here, such as an example of typical shapes of microplastics showing literature, and in order to see the typical shapes or size that are reporting from different scientific studies. So well, with this problem, as I said before, the idea is to, with Preserve, to give an approach or an alternative for the specific case of recycled nonwovens, or nonwovens made from a recovered material that is more likely to release microplastics or particles in a very low size that can contaminate the environment. So the idea, first of all, was to select representative nonwovens of this type of substrates, because the idea is to use in the forthcoming months a substrate coming from all the procedures of end of life during the project. The main candidate that we have now is to use a PLA, a recovered PLA from packaging manufacturing. And the idea is to manufacture from this waste of PLA from PLA trays, manufacture fibers in order to obtain a nonwoven based on this PLA recovered. And the idea is that we will test the finished coating in this substrate. But in the meantime, in all the lab experimental work that we performed in the 1.5 first year of the project, we selected different nonwovens representative as recycled nonwovens or biodegradable nonwovens. That's why we selected a PLA, a commercial PLA, and also 2 references of recycled polyester of the different grammages, between 80 and 145 grams per square meter. So well, with these 2 selected nonwovens, on the other hand, we also selected different bio-based finished coatings that can be applied on these nonwovens. Also, one of the objectives in Preserve was that these finished coatings had to be bio-based by nature. That's why we selected, for example, PLA resins, polysaccharides, bio-based polyurethanes, or other type of bio-based resins that could be applicable by conventional methods of printing or coating applicators for this type of substrates based on nonwovens. So well, at lab scale, the idea was to test all these finished coatings on these nonwovens using lab coated applicators in order to obtain coating nonwovens for the characterization trials. We use two types of coating application methods, one of them based on Baker or white bars with a specific height of coating, another type of coating applicator based on a deep coater. After that, all the coating nonwovens that we obtained were performed according to different parameters in characterization trials. On the one hand, we study the abrasion resistance in order to evaluate the integration of the coating nonwoven against different textiles. For example, we use wool and denim. Other type of resistance that we study was the coating fastness in order to study the after a specific washing procedure if the coating remains in the nonwoven. And also with the help with Centex Bell, which is a partner of the project, we quantify the fiber release after the finished coating is applied on the nonwoven. And lastly, in parallel, we also study the co-toxicology of these finished coatings in the nonwovens with two types of analysis. In vitro test with daphnias and algae, and also using a specific methodology which is called mesocosm in order to simulate a specific ecosystem, an aquatic ecosystem, and to evaluate the influence in this ecosystem of the toxicity in case of it has toxicity of these new materials. So well, with all of this, we obtain as best candidate or the most promising coating nonwovens these references with the different types of nonwovens, and the main candidate was finished coating based on PLA resin and also a polysaccharide. So here we have the main or the ranges of solid content of each finished coating, and also the viscosity that we recorded, and also the dry weight, the dry weight of the coating nonwoven that we obtained, because all these parameters are very important in order to these coatings can be scalable in the next steps during the project. So well, in all this part, we were in contact with Centex Bell, which is the partner that in the forthcoming months will scalable the application of these finished coatings in order to obtain the final materials in the project. Also here you have some examples of the coating nonwovens, and at the end the prioritized coating application method was the Baker bar, because with the deep coating the dry weight, the quantity of coating applied was too high, and at the end it was more brittle, and all these materials had less resistance than other ones applied with this application method. So well, after that, and with all of these materials, we perform the abrasion resistance and the color fastness, and with all the materials passing these tests, we perform with the help of Centex Bell the microfiber release quantification. The idea is to use a standard which is called the test linting test, which with a mechanical procedure quantify the fiber that are the microfiber release during the process, and we have the quantification depending on the size of each particle that is released. Our main focus on the project was in all the particles released up to upper than the 0.3 microns. So what we performed during the project was to compare the uncoated nonwoven based on PLA or polyester against all the coating nonwovens based on a finished coating of PLA or based on polysaccharide. So here you have the values, and the main conclusion is that from polyesters, the reduction was higher using the finished coatings. Even with PLA and the coated PLA, also we could show a reduction, but less than with the coated polyester, where we could achieve up to 7 or 80% of reduction against the uncoated nonwoven. So, well, this was the first step and the main important in order to select the materials that could be applicable for the next steps in the project for developing the demonstrator in all the scale-up process that is planned for this last year of the project. As I mentioned before, also the idea was to test the toxicology of all these materials, and this is the results that we obtained in terms of in vitro tests against Daphnia and algae, and also in the specific test simulating the aquatic ecosystem. And as we saw is that mostly all the materials tested passed all the tests in the characteristics that we obtained, because here is also important the quantity of the coating applied. So, well, as I mentioned before, the application method that we use achieve enough finished coating to reduce the microfluidic release, and also to not give toxicity for the system. Apart from a specific case in terms of polysaccharide against Daphnia, which gave toxicity in this specific case. So, well, in order to move for the next step in the project, which is the scale-up and validation, first of all, what we did was to summarize all the results obtained from the lab and to prioritize the most candidate finished coatings that we have used to scale up and to initiate the validation in an upper scale in the project. Because, as I mentioned before, now we are in the middle of the scaling up of this part in the project with the developing of all the demonstrators in the project. But previously of that, we initiate a little validation in an upper scale in our facilities. Specifically, regarding the results and also the availability of the materials, we selected the PLA-based finish coating in a specific polyester in one of them, and we performed an upper scale coating application with a pilot printer machine that we have in Itene, with a specific wet coating application, and with 2 ovens with different drying up to 60 degrees and with a speed of 8 meters per minute. We obtain a coated roll of the polyester nonwoven, the recycled polyester nonwoven, and we characterize this roll in similar way as all the materials that we tested during the lab experimental work. Here you have the results. We could also obtain a dry wet more or less similar or quite close to the 7.5. We obtain a 5.6 of grams per square meter of the coating nonwoven, and with this finished coating we could test it a reduction in the microplastic release of an 88% of reduction, even a little bit higher than the similar material developing in the lab. And in the same way, we also tested the co-toxicity and the mesocosm analysis, and we proved that the material also was non-toxic. So, well, the idea here with this initial scale up is continue with the scaling up in the project, which, as I mentioned before, Centex Bell is the responsible for that part in order to obtain the PLA recovered from the project and to obtain this nonwoven based on PLA, and the applicator of this PLA-based finish coating in their pilot machines. With this final material, the idea is to shape a shopping bag as demonstrator of this part in Preserve, with this finish coating applied, in order to perform the final characterization of the material, which again will be performed by Itene, and to, hopefully we will expect to validate the results and also to test them in a real recovered material from the project based on PLA. So this is all the information and all the the results that I wanted to share with you. Please, if you have any questions or doubts or any issue regarding this part, don't hesitate to contact me. Thank you very much.
Thank you, Teresa, for this very informative presentation. The session for questions and answers is now open for any participant who wants to make any comment or questions. Raise your hands or use the chat box. Can't see any hands raising. So I think we explained it very well with all the process that Preserve is actually working on. So I don't know if Natasha, would you like to wrap up the webinar and
Of course.
some concluding remarks? Yeah.
Can you hear me?
Yes, we can.
Okay, thank you very much to everyone for these great presentations. And I can say that this webinar provided valuable insights into various aspects of plastic pollution and sustainable solutions. All presentations shed light on different perspectives, including the emergence of microplastics as an environmental pollutant, then the importance of upcycling plastics for a circular economy, the role of microbial communities in utilizing polymers and sustainable solutions for plastic bio-upcycling. That were all a presentation that we heard about, and I can say that we had opportunity today to hear about first the growing concern of microplastics as an emergent environmental pollutant. This first presentation emphasized the need for concentrated efforts to address this issue, such as implementing proper waste management practices, then promoting eco-friendly alternatives, and the most important, raising awareness among individuals and industries. But also it is very important the standardization of the method for the analysis of microplastics, because without a standard method we cannot have comparable results, and we cannot speak the same language when it comes to environmental pollution with microplastics. And the second presenter today focused on the sustainable upcycling of plastic for a circular economy and a greener environment. It stressed the importance of reusing and repurposing plastics instead of their disposal, which can significantly reduce waste generation and minimize environmental impact. Examples of successful upcycling initiatives and innovative technologies were highlighted, and I hope that inspire the audience to explore similar approaches. Also today we heard about the fascinating world of microbial communities and their ability to utilize polymers as a substrate. Our presenter discussed how these communities possess unique enzymatic activities that can break down plastics, offering a potential solution to plastic pollution. And the presentation also touched upon ongoing research and the challenges associated with harnessing microbial capability effectively. Then we received information about upLIFT project and its sustainable solutions for plastic bio-upcycling. Our presenter shed light on the use of biotechnological approaches, including enzymatic degradation and bioconversion to transform plastic waste into valuable resources. And this approach provides a promising avenue for reducing plastic pollution and creating a more sustainable future. And lastly, the fifth presentation emphasized the importance of finish coating to reduce microplastic release from recycled textiles. And it showcased innovative techniques and materials that can prevent the shedding of microplastics, ultimately reducing their presence in the environment and safeguarding ecosystems. Overall, the webinar addressed significant issues related to plastic pollution and presented a range of sustainable solutions. And the knowledge shared in the presentations calls for further research, collaboration, and implementation of these ideas. I can say that by working together, we can chart a path to a cleaner and more sustainable future. We received very useful and usable informations today, new ideas about possible cooperation between projects, and maybe we will have a joint application, maybe for a new project. And as our colleague said, the new working groups for some topics that are common to all partners. So once again, thank you to all presenters and to organizers of this webinar. And I hope that this is first but not the last webinar.
Thank you, Natasha. Few comments from Fuensanta and Debolena. Fuensanta, would you like to start?
Yes, well, after this webinar, it is clear that we are facing common challenges. So there is room for collaboration. We've seen that we need standardization to develop a specific methodology. We've seen that we are facing similar problems in life cycle assessment. And also we all has highlight the importance of citizen awareness. We presented 2 weeks ago our citizens awareness platform. You can visit it in our webpage, in upPE-T webpage, and we are open to receive any material that you think it is useful for citizen awareness. And we invite you to participate in the forum of the platform and also in the blog. So if you have nice information to share with citizens in general to promote more sustainable behavior, please send it to us, because we are we are willing to upload all this interesting information, okay, to filling of content this platform.
Thank you, Fuensanta. I have posted the ECAP website in chat. Debolena?
Yes. My comment is related to communication and dissemination, actually communication. So what I can see that today's webinar is very successful, and starting from the organizer to the speakers, it's all women group. So all lady bosses basically. So we can highlight that fact. In fact, one of our partners, Fabiola, I think she's also present in the webinar. So she posted something on LinkedIn related to that, but we can do it from our official channels as well. That, yeah, because the European Commission gets excited when there are a lot of women participating in research projects. So yeah, just that we can capitalize on that. And thank you, everybody, all the speakers, organizers, and also attendees.
Thank you all. I don't know if there are any comments before we close the webinar and say thank you to everybody. A special thank to the Institute for Development and Innovation and Nina Makarevich, who's organized and brought you all together. We have a message from the Preserve project who saying that they're hosting a workshop in Berlin on the 11th of December. The event is called The Future of Bio-Based Packaging, Co-Designing a Roadmap to 2030. So use the link that has been provided in the chat box to register in this workshop if you wish. Before we close, I would like to share the contact details of and the social media of all 4 projects that have been participated in today's webinar. So you can visit the websites, you can have a look at the social media and the posts that the projects are sharing. And if we don't have any other comments, we can close this meeting. And I would like to thank you all for attending, for your patience. It has been a very interesting 3-hour webinar. It will be available on our YouTube channel, and we will, of course, share it through our social media accounts. So thank you everyone again, and we will hopefully see each other again in next workshops or webinars like this. Thank you all.
Thank you, Angela.
Okay, thank you.
Thank you. Bye-bye.
Thank you.
Bye.
Bye.
Thank you. Bye-bye.